All right, let's go ahead and take a look at section 3.9, logarithmic differentiation. Okay, what we're going to do in this section is build on the idea that we built up a little bit earlier on implicit differentiation. So we're going to start by looking at taking derivatives of exponentials and logs. We talked about this a little bit in an earlier section when we said the derivative of e to the x is just e to the x. Okay. What we're going to do in this section is we're going to explore this a little bit more so. I don't want to go into too much depth about why the derivative of e to the x is e to the x. There's, kind of a fun numeric exploration of that. Part of it is, we kind of define things that way, right? So if there's different bases of exponents, right? If I look at y equals 2 to the x, right? Then I get a graph. Okay. If we look at on the same graph y equals 3 to the x, we'll get a graph that is similar but a little bit steeper. Okay, and if I looked at, say, y equals 10 to the x, okay, that would be even steeper yet. Okay, and all of these are going to have a different slope of the tangent line at x equals 0, right? So they all have some sort of tangent line. Right? If I look at the 2 to the x1, it's like here. It's not very good, but we look at the 3 to the x1, it's like here. So the idea is by changing the number base, I can get a different slope of the tangent line at the origin, right? So if I were to look at maybe think of this as like a sliding scale, one of these would have a slope of the tangent line as 1 at the origin. The reason that that's important is because if I try to find the derivative of an exponential function, so let y equal b to the x, where b is some number. And we want it to be positive, okay? Then if I take the derivative using the limit definition, I would have b to the x plus h minus b to the x all over h. Okay, and I would use my properties of exponentials to break that up into b to the x times b to the h. And I would factor that b to the x out. Okay, and what I have here, this limit as h goes to 0 of b to the h minus 1 over h. That's 1 is, this function with 0 plugged in. Okay, so a way that I could rewrite this is b to the h plus 0 minus b to the 0 all over h, which is just the derivative with 0 plugged in. Okay, so we could think of this as being like y prime of 0. So what ends up happening is if I look at the derivative of b to the x, I get b to the x multiplied by whatever slope of the tangent line I get at x equals 0. And so if I pick b to be a number where the slope of the tangent line is 1, then the derivative will just be that function. Okay, and so one of the ways that we can define the number e is it's just the exponential that gives us that 1. Okay. Okay, so we define e to be the number of the exponential function. Whose slope is 1 at x equals 0. Okay, and that's, I don't know if that's a real satisfying way to think about this number e, and there's more ways to go about it, but you know, we can experimentally verify that this e to the x, or you know, this number e that we get does indeed turn out to be, you know, this 2.718 business that we're used to for e. Okay, so that's how the derivative of e to the x is e to the x. So let's expand that a little bit and say, okay, what about for other number bases? So what is the derivative of a to the x for other numbers? A. And the way that we can figure that out is by taking our a to the x function and making it look like an exponential again. Okay. So let's suppose my function f of x is a to the x. Okay. Well, this might be easier to do after we introduce the log and look at the derivative of a natural log. But one of the ways that we can deal with the a to the x is to turn it into like an e to the x looking function. Let me just grab my pen here. So let's go ahead and see what that looks like. So recall that because of inverses, the natural log of e to the x is just x, and e to the natural log of x is just x, right? They undo each other. Okay, so one of the things that we can do is we can take this x and, oh, here, let's rewrite this. Right, this is y equals a to the x. Okay. I can take any number and just take, you know, e to the natural log of that thing. So we could write this as e to the natural log of a to the x. And then we can use our properties of logs to take this x and bring it down out front. So this is e to the x times ln of a. Okay. And now if I wanted to differentiate it, this is now going to be e to some function of x, so we can differentiate using the chain rule. So f prime of x is, when I differentiate, I'm going to get e to that same function times the derivative of the inside function. And since ln of a is just a constant, the derivative of x is 1, we just get ln of a here. Okay. And going back up here, e to the x times ln of a is the same as writing a to the x. So I could rewrite this as a to the x times ln of a. So we get another derivative formula. The derivative of a to the x is a to the x times ln of a for a constant a. And the a has to be positive because otherwise exponential functions don't really make sense when you use negative values. All right, so that's derivatives of exponentials. Now let's look at logarithms. Okay, so let's start with f of x equals the natural log of x. Okay, or it might be nicer to write it as a y equals, just for what we're going to do next. I don't know, the derivative of natural log of x. I want to find that out, and I don't want to use the limit definition. So one of the things that we can do is leverage what we already know about exponentials. So I'm going to take e to the power of both sides so that this equation becomes e to the y equals e to the ln of x, which is just x. And now we're going to use implicit differentiation. Okay, so on the left, when we use implicit differentiation, the derivative of e to the x is e to the x. So here I have a function of x. When I differentiate, I'm going to get that function. And then the chain rule says multiply by the derivative of the inside stuff. Well, the inside stuff is y, so the derivative of y is dy dx. On the right, when I differentiate, I get 1. So solving for dy dx, I get dy dx equals 1 over e to the y. And what I have written right here is that e to the y is the same as x. So when I started with a function ln of x, the derivative is 1 over x. So when we take the derivative of natural log of x, you get 1 over x. Okay, just like we did a minute ago, we can also look at the derivative of logs that use other number bases. Oops, that's not what I wanted at all. All right, so now let's look at other number bases. So suppose I have a function g of x that's log base b of x. Okay, we're going to do something like we did with exponential. We're going to turn this back into a natural log. Right? We'll change the base back. And there's two ways to go about this. I think that the easiest way is actually to leverage our change of base formula. And that says that log base b of x is ln of x over ln of b. Okay, and so you might remember that from algebra or pre-calculus. Okay, and if we use that, then g of x is ln of x over ln of b. So then g prime of x, when I differentiate ln of x, I get 1 over x. And this ln of b is just a constant, so it just hangs out. Okay, so when I differentiate my exponential function that's not base e, we get a natural log of that base multiplied in the numerator. When we differentiate a logarithm that's not base e, we get the log of that base except in the denominator, right? Because it's backwards. Okay. So again, as a derivative rule, the derivative of log base b of x It's 1 over x times ln of b. All right, let's look at a couple examples to illustrate what's going on here. In particular, get some experience with the chain rule. So let's suppose we have a function e to the 3x squared plus 4x, and we want to find the derivative. Okay, so I'm going to use the chain rule. Where the 3x squared plus 4x is my inside function. Okay, so when we differentiate it, the chain rule says take the derivative of the outside. Well, my outside function is e to the stuff, and I know the derivative of e to the x is e to the x. So nothing changes. I don't plug in x, I plug in my inside function. And then chain rule says multiply by the derivative of the outside, or sorry, of the inside. So we'll get e to the 3x squared plus 4x times 6x plus 4. And that's it. Right. If I take the derivative of a logarithm, let's look at an example of that. Suppose g of x is the natural log of sine of x plus x squared. Okay. This is also a chain rule. Because I can see an inside function and an outside function. So when I differentiate here, the derivative of natural log of x is 1 over x. Using the chain rule, I say, okay, I'm going to follow that rule. I take 1 over x, but instead of x, I plug in the inside function. And then we multiply by the derivative of that inside function. Okay. The derivative of sine x is cosine x. The derivative of x squared is 2x. And what I can do is I can rewrite that as a single fraction. I can write cosine x plus 2x all over sine x plus x squared. What we typically do when we have a natural log and we're differentiating, instead of thinking of it as being 1 over the inside stuff times the derivative of the inside stuff, and then putting that other stuff in as the numerator later, we can do that all in one step. For y equals the natural log of some function of x, we can write that the derivative is f prime of x over f of x. Okay, so that's just the chain rule and then smooshed together, right? Instead of writing 1 over f of x times f prime, we just write f prime of x over f of x. Okay. All right, let's look at another example. Let's suppose I have a much more complicated function. Okay. I'm going to show you two different ways to do this problem. I'm going to show you a difficult way that I don't recommend on the left. Okay. And then I'm going to show you a much easier way on the right. Okay, now both of these are going to be a complicated derivative. They'll both be correct, but you'll see why we want to use the easy way. The hard way to do this would be just to start by differentiating it. So I write f prime of x, and that's going to be 1 over the inside function, and the inside function is a fraction. So I have x squared cosine x over 3x plus 2 squared times 9 minus x, okay, times the derivative of the inside function, and I'm going to write that in the numerator. Okay, so I have the derivative of x squared cosine x over 3x plus 2 squared times 9 minus x. Okay, the derivative of that fraction requires a quotient rule. Now, to save myself on some writing and a little bit of confusion, instead of writing divided by this fraction, I'm just going to multiply by its reciprocal. Okay, and now we're going to take the derivative of this, and I'm going to be, I'm not going to write out every step in painstaking detail because there's a lot of steps, but we're doing a quotient rule. Okay, so we have derivative of the top, we have the derivative of x squared cosine x times the bottom left alone, and the bottom is 3x plus 2 squared times 9 minus x, okay, minus the top left alone times the derivative of the bottom. Okay, and then the rest of the chain rule is we have the denominator, 3x plus 2 squared times 9 minus x, and that whole denominator gets squared. Okay. Now we're going to have to be real careful because things are going to get more and more complicated as we go. So I'm just rewriting this beginning part. When I take the derivative of x squared times cosine x, that is a product rule. So inside of here, I have the derivative of x squared, which is 2x, times cosine x, plus x squared times the derivative of cosine x, which is negative sine x, times 3x plus 2 squared times 9 minus x. X squared cosine x over here is left alone. And then over here, I'm taking the derivative of 3x plus 2 squared times 9 minus x. Because that's a product, I'm going to use the product rule. So I take the derivative of 3x plus 2 squared, which is a chain rule. So we have 2 times 3x plus 2 to the power of 1 times 3 times the 9 minus x left alone, plus 3x plus 2 squared left alone times the derivative of 9 minus x, which is negative 1. Okay, and then in the bottom we'll have this 3x plus 2 to the 4th, 9 minus x squared. And at this point, I'm just going to stop. There's a lot of simplifying that you can do, but I'm done differentiating. And there's a lot of little details that we had to be careful of, and this is a big mess. Okay, so this is the hard way. We don't want to do this. Let's look at an easier way to do the same problem. I'm not going to start with the derivative. We're going to start with f of x, and we're going to use the properties of logs to break this up. So what I'm going to do is say, well, I know my properties of logarithms. If I have two multiplied things, we can break that up into ln of a plus ln of b. If I have two divided things, that breaks up into subtraction. And if we have an exponent, ln of a to the power of b, that b can come out front. Okay, we're going to use all three of those rules here. I have a fraction, so we'll break that up into subtraction. We have multiplied pieces. We'll break that up into addition. And then we have powers that we'll bring out. So starting with the fraction, I can write this as ln, stay consistent with the color here, ln of x squared cosine x minus ln of 3x plus 2 squared times 9 minus x. And then I'll use my multiplication into addition property. Write this as ln of x squared plus ln of cosine x minus ln of 3x plus 2. Now, what I'm really doing is I'm taking this and turning it into two added things, but they're both subtracted here. So I'm going to distribute this negative and make them both subtracted. And finally, I'm going to use this third property to bring powers down out front. So this is 2 ln of x. The ln of cosine x just hangs out. My squared. The 2 from the squared comes out. And nothing special happens with the 9 minus x. We haven't done any derivatives yet. This is still the original function. So now we're going to differentiate. I'm going to skip down a little bit just because I've used up all of my space with the other derivative. So let's look at f prime of x now. The derivative of ln of x is 1 over x. Okay. Here I have a chain rule. The derivative of ln of a function of x, we take 1 over the inside function. It's 1 over cosine x times the derivative of the inside. The derivative of cosine x is negative sine x. Same thing with the next one. Take 1 over the inside function times the derivative of the inside function. 1 over the inside function times the derivative of the inside function. And now I'm done. Again, there's some simplifying that I can do, but I'm done differentiating. And not only does my result look a lot cleaner and easier to write down, but the individual steps were a lot easier. So breaking it up with algebra, took a little work before we started the derivative. But then my derivative, the worst I was stuck with was a chain rule, right? I had a couple of chain rules, maybe 3 chain rules, but there was nothing like nested going on. As opposed to, here we had a quotient rule, and inside that quotient rule was a couple of product rules and a few chain rules, and all mushed together creates a lot of opportunity for mistake. So when we take a derivative of a logarithm, we can use the properties of logs to help us differentiate. Okay, I'm going to take that to sort of the next level here. Let's suppose I have a function that doesn't have a logarithm in it, but it's a complicated mess of multiplying and dividing and powers and stuff. So let's suppose we have this function y equals x cubed times 3x plus 2 to the 5th times x squared plus 1 to the 4th over 4 minus x squared cubed times 5x plus 1 to the 6th. Okay, once again, we could differentiate this using our derivative rules. We don't need a logarithm, but it's really complicated, right? We have a quotient, we have a triple product on top. That's a real mess. Product and bottom, and there's chain rules everywhere. Okay, so what we're going to do before we take a derivative is we're going to use logs to help us. So I'm going to introduce a logarithm. I'm going to take log on the left and log on the right. So all I did was take the log of both sides, but now on the right-hand side, because all of this is in a logarithm, I can use my properties of logs to break it up. So let's do that. Okay. Now, what you noticed before when we used our properties of logs was that the multiplied pieces are just going to be added pieces. The things in the denominator are subtracted pieces, right? Because in the division we subtract. So I'm not going to do this as two separate steps. I'm going to combine those two and write this as ln of x cubed plus ln of 3x plus 2 to the fifth plus ln of x squared plus 1 to the fourth, and then minus ln of 4 minus x squared cubed minus ln of 5x plus 1 to the sixth. And then I can use one more set of properties of logs to bring the powers down out front. And what this does is it takes off a layer of chain rule on each one of these. Okay. So now when we differentiate, on the left, this is a function of x, right? Y is a function of x. So here we use implicit differentiation. Okay, so the derivative of ln of y is going to be 1 over y times the derivative of y, which is dy dx. And on the right, when we differentiate, we're doing a normal derivative, and we have all these little pieces, right? So I have 3 times 1 over x plus 5 times 1 over the inside stuff times the derivative of the inside stuff. The derivative of 3x plus 2 is 3. Okay, 1 over x squared plus 1 times the derivative of x squared plus 1. 1 over 4 minus x squared times the derivative of 4 minus x squared. 1 over 5x plus 1 times the derivative of 5x plus 1. Okay, I'm done differentiating now, but with implicit differentiation, we have to solve for the derivative. So I solve for dy dx, and I'm going to do that by multiplying by y. Okay, but I don't want to leave y in my answer because we started off with an explicit function, right? There were just x's in my function. So I want to end with just that. So what we're going to do is I'll write y here for a minute, but I'm going to erase it. So I'm just rewriting this, maybe doing a tiny bit of simplifying here. Not canceling anything, I'm just multiplying the numbers up. Okay, but instead of writing a y here, what we can do is we can say, oh, replace y with what it's actually equal to. So I'm going to erase the y and instead write, since we had y equals this big fraction, I'm going to write the x cubed times 3x plus 2 to the fifth times x squared plus 1 to the fourth over 4 minus x squared cubed times 5x plus 1 to the sixth. Okay, that's still a messy derivative, but it would have been ridiculously difficult if we hadn't used a logarithm to help us break it up. Okay, this process of using a log to help differentiate is called logarithmic differentiation. Okay, and that's not only where our section gets its name, but this sort of completes the process of derivative rules so that we can take the derivative of pretty much anything that you could write down. Okay, so I'm going to give you an example now of a function that we can't differentiate without logarithmic differentiation. And I'm going to start by writing the simplest function I can think of that does this. Okay, so y equals x to the power of x. Now, before I start differentiating this, what I'd like to do is make some comments about it, because if I were to give this to a class of calculus students, there are a few mistakes that would be very common to see. So one thing that people might do is look at that and say, well, I see an exponent, bring the exponent down and lower the exponent by 1. Okay, and that's the power rule. So let's review the power rule really quickly. So here's the power rule. The derivative of x to the n is nx to the n minus 1. Okay, this works for power functions where the power is a fixed number. Okay, in x to the x, my power is a variable, so this is not a power function. Okay, the other common way that I see this function differentiated incorrectly is to think back to where we started this section, and we said, oh, we can take derivatives of exponentials that are not base e. Okay, so let's look at the exponential rule. Right, that said that the derivative of a to the x was a to the x times ln of a. This works for constants a, in particular constants that are greater than 0. Okay, so in order to be an exponential, the base has to be a constant, and this is not. So this is not an exponential function. So we cannot use either the power rule or the exponential rule on this function. And that's where this becomes a little bit challenging, and that's why we need logs to help us out. The logs can break up the power here, where I don't have a constant as either the base or the exponent. Okay, so let's use logs. I'll take the natural log of both sides. Ln of y equals ln of x to the x. And then what I'm going to do is use my properties of logs to bring the exponent out front. That property of logs works on anything, whether it's a constant or a variable. So we have ln of y equals x times ln of x. Now we use implicit differentiation. Okay, on the left, my inside function is y, the outside function is natural log, right? When we differentiate the outside, it says, okay, take 1 over the inside times the derivative of the inside. The derivative of y is dy dx. On the right-hand side, we have to do a product rule. So we have the derivative of x times ln of x plus x times the derivative of ln of x. The derivative of ln of x is 1 over x. So simplifying here, I have 1 over y times dy dx equals ln of x plus 1. X times 1 over x will just give me a 1. So now we multiply by y. So on the left, the y times 1 over y cancel, and we have our derivative dy dx. And on the right, we have y times ln of x plus 1. Just like we did in the past, we don't want to leave the y here. We're going to get rid of it. And at the beginning, we started by saying y is equal to x to the x. So we replace the y with x to the x. So there's our derivative. Okay, and that's the process of logarithmic differentiation.